Hello, and welcome to this presentation on a faster reachability analysis for LR1 parsers. I am Frédéric Bour, a PhD student, and this is a joint work with my advisor François Pottier. Here is the plan. First, I will introduce the reachability problem. Then, we will look at the current state-of-the-art solution and see how we improved over it. After that, I will give an overview of the main idea of our contribution, and then we will conclude. So what is LR1 reachability and what is its purpose? The problem can be defined as whether it is possible to reach a specific configuration of the automaton. Configuration is a pair of a state and an unconsumed lookahead symbol. So we want to know whether there exists a sentence that brings the automaton from the initial configuration to the desired one. And in practice, we also want to know the shortest sentence. Why would we solve that problem? The first main category of applications is the generation of test cases. We are interested in negative test cases, generating a list of sentences to reach all states that can fail. This idea goes back to a paper by Jeffery in 2003, which suggested an approach to write error messages for LR parsers. Much of the work was manual, and Pottier proposed a methodology to automate a part of the work and guarantee completeness of error coverage. Reachability is a core component of this approach. For instance, here is the specification of an error message for C grammar. The first part specifies a sentence that ends in an error. It is produced by the algorithm. The last part is a corresponding error message written by the grammar maintainer. Of course, positive test cases are also possible for regression testing, compatibility checking, etc. Finally, this method can also be applied to provide syntactic completion and error recovery. What is the state-of-the-art solution to this problem? In 2016, Pottier proposed an algorithm that he implemented in the main-here parser generator. It was successfully applied to the front end of Concert, a verified C compiler. The sample message from the previous slide was taken from it. Unfortunately, it does not scale well. Here is a graph plotting the time and memory consumption of the algorithm for different grammars. The scale is logarithmic on both axes. On the axis, we jump from 10 to 1000 seconds, and on the ordinate, from 100 megabytes to 10 gigabytes. For realistic grammars, it can be quite consuming. Concert C grammar takes 25 seconds and half a gigabyte. Unicon grammar takes almost 10 minutes and 8 gigabytes. This restricts the possible applications to batch use cases, and it can be a burden for grammar maintainers working on error messages. We observe that the algorithm works in two main steps. First, for each transition it will try to compute the shortest input. Second, it produces minimal sentences by repeatedly taking transitions. The bottleneck is by far the first step, so that's what we focused on. Now, let's see our contribution. This graph will compare the performance with our new algorithm. The blue triangles represents Pottier's algorithm performance. This graph is also in log-log space. A gradation represents an order of magnitude. On the left, you see the time consumption, and on the right, the memory consumption. We add our first algorithm, depicted with red rectangles, which we call the naive cost matrices. Points on the same vertical line applies to the same grammar. The first surprise is that it already improves the runtime significantly. On the left, the red cloud is below the blue cloud. But it consumes a lot more memory. On the right, the red cloud is above. Fortunately, it is also amenable to a lot of optimizations, and we introduce our final algorithm, the compact cost matrices. The green cloud is really low, both for time and memory. It beats the other algorithm by 2 to 3 orders of magnitude. To get an idea of the practical impact, here are the new figures for our reference grammars. Both are processed in a fraction of a second without using much memory. In our experience, it performed as well for most mainstream grammars, Java, JavaScript, C++. However, we found a few ones that are still expensive. The C++ grammar from Hashimoto and Mori supports many C++ dialects and extensions, and include cleverness to handle common preprocessing patterns, resulting in a very big automaton. It takes a bit less than a minute and 3 GB of RAM to process. Let's talk about our changes. The first idea is to use matrices to represent intermediate results, and it leads to the naive cost matrices algorithm that we saw on the previous graph. We will start with this LR1 grammar to illustrate the approach. It has two non-terminal symbols, S and T, and two terminal symbols, A and B. S is the entry point and has two productions, TA and TBB. T also has two productions, A and AA. It turns into the following automaton, starting from state S0 and recognizing S. However, there is a shift-reduce conflict. After shifting A, we reach state S5. In this state, when looking ahead at another A, we can either reduce the production T equal A, or shift the A and get to state S6. In this example, we decide to shift. The reduction looking ahead at A disappears. The only way to reduce T equal A is now to look ahead at B. Now, we will try a first attempt at defining costs. Cost is a function that gives us the length of the shortest input that permits to follow transition starting from its source state. Let's start with the trivial cases. Shift transitions. To shift A from state S0, the cost is 1. We only need the symbol A. Actually, it's the same for all shift transitions. Things get interesting with go-to transitions, labeled with non-terminals. To recognize T from state S0, we need to reduce either T equal A or T equal AA. The cost of the reduction is the sum of the costs of the sequence of transitions, and since we are interested in the smallest cost, we take the minimum. Here, it will be 1. And finally, we look at recognizing S. There is also two reductions, S equal TA and S equal TBB. We compute their costs, take the minimum, and we get 2. But this is wrong. Because of our conflict resolution, the minimum for T is reached when lookahead token is B. But in the shortest production for S, T is followed by A. So we will revisit our notion of cost. A single integer is not sufficient because we need to keep track of lookahead tokens. We propose to use matrices indexed by terminals. The row indexed represents the lookahead token before taking the transition, and the column index represents the lookahead token after taking the transition. For instance, this cell will contain the cost when entering and exiting a transition with lookahead A. This one, the cost when entering with lookahead A and exiting with lookahead B. And similarly when entering with lookahead B. This approach composes. Using the min plus summering, matrix products represents the cost of a sequence. Let's update our equations with matrices. First, the cost of shift transitions. They get a bit more interesting. The matrix for transition on A have 1 on the line indexed by A and plus infinity everywhere else. We add infinity to represent unreachable cases. A shift transition can effectively be taken only when looking ahead at the same symbol. And it doesn't matter what token comes after shifting. The whole line is 1 because there is no constraint on what follows. The same goes for B, with the one line moved to row B. Now, the non-terminal cases. We keep the same equations, replacing addition with matrix product. We see that the dependency on lookahead tokens is preserved, and finally, we get the right cost. That is nice, but consumes a lot of memory. T by T is a lot on complex grammars, and we need a lot of matrices. It is also wasteful. In many cases, we don't need to distinguish all terminals. In our example, It is the conflict resolution that makes cost computation more involved. We can characterize and group tokens with identical behavior. The precise definition is in our paper, but we will illustrate it with an example. How can we group terminals? Let's look at transition S0T. It is followed when one of the production of T is reduced. Production T equal A is reduced only when lookahead is B. Let's write down the set B. Production T equal BB is reduced no matter what the lookahead is. The associated set is AB. The different cases that need to be considered for the transition is the coarsest partition of terminals that refines the sets we found. The classes corresponds to the possible reductions that lead to following the transition. For the class containing A, the only reduction is T equal BB. For the class containing B, either reduction is possible. Applying the same classification to the transition S0S gives the partition that contains the set AB. Both are in the same set because we don't need to distinguish between them for this transition. This is sound with respect to the matrix we computed earlier. Both columns are equal, we didn't lose any information. So before even starting to compute the costs, we know what lookahead symbols need to be distinguished. This leads to our second idea, compacting matrices. In this example, we will look for a more compact matrix that keeps all the necessary information. Let's assume that we have 4 terminals, A, B, C, and D, and that our characterization found that columns A and B belong to the same class. As predicted, we see that columns A and B are equal, so we will merge them. After merging, the columns are now indexed by classes of a partition of terminals. Now, let's assume that our matrix M with merged columns AB is post-multiplied by another matrix. We will focus on the first cell of the resulting matrix, RAA, the product of this line and this column. If we unfold the matrix product, we find the following equation, where the wedge operator denotes the minimum function. We know that XAA equal XAB, since we merge the columns. Therefore, we can rewrite the first terms to factor out XAA. We apply this rewriting to the equation, and now we see that the terms YAA and YBA appears under a minimum. Actually, they always appear under a minimum in the definition of R. No cell depends on YAA or YBA alone. Thanks to the properties of minimum, when columns are merged in the left matrix, only the minimum of the matching lines in the right matrix is ever observed. We can directly compute the minimum and never represent the whole matrix. Just like we merged columns before, we can now merge lines. Finally, we have matrices where rows and columns indices belong to partitions of terminals. This improves consumption significantly. We observe, on average, a reduction by 5 orders of magnitude. We brushed over many details. To get a practical implementation, one will need to deal with many more issues. First, real-world grammars are recursive, and solving cost equations is a bit more involved. Still, the equations have nice properties that make it possible to solve them efficiently. Then, as we have seen, we have to represent and compute many partitions of terminals for each matrix. This can be delicate, both in space and time, and specialized algorithms are helpful. And finally, many tricks can speed up the implementation, such as reordering and sharing matrix products. You can find all the details in our paper. Now, to conclude, we propose a new algorithm for computing reachability in LR1 automaton that performs significantly better than the state-of-the-art. To do so, we proceeded in 2 steps: reframing the problem in terms of recursive matrix equations, finding a way to make the matrices much more compact, reducing both time and space needs. We implemented and tested extensively and got very good results, and this should be available soon in the Menhir parser generator. Thanks for your attention.